Check it out now, y'all.
nanoHUB-U online instruction.
Hi, I am Edwin Garcia. This is the second lecture from nanoHUB-U on the material science of batteries. Today's lecture is the charge figures of merit in a rechargeable battery. Okay, in the last lecture, we were talking about the reactions occurring between the anode and the cathode. During that reaction, that there's a species S that it's exuded into the electrolyte, which is balanced, or it's being taken by the cathode itself in order to accommodate that species. And through the electrolyte, that species is being shuttled back and forth. Okay, while outside the entire system, we have our load or a resistor through which those electrons are giving us actual useful work. Okay, we were discussing in the context of the energetics how the voltage in the anode and the voltage in the cathode was giving us the actual potential of the entire cell. Today, we were going to be talking about, we're going to be detailing this picture and how that impacts on the performance of the cell. I want you to think first that when you're taking an ion out of the anode and putting it into the cathode, that occupies some space in the cathode. You actually have to open up the lattice and squeeze the ion in there, okay, as it reacts with the electron. So there are so many ions that you can put in the cathode. Basically, there's a limit of a material that you can dissolve in it. There is a solubility limit on how much charge you can effectively store in the cathode. And by the same token, there's a certain amount of mass or charge that you can store in the anode. Each of them, therefore, specify the anode solubility limit. You can think of it as a number of how many moles of material of species S per meter cube you can store here, and how many moles per meter cube you can also store in the cathode. If you think about it, what you really would like is a very well-balanced system, because you want to move as many of these ions as you can from the anode and putting them into the cathode and back. Okay. In practice, however, the non-idealities, the specific chemistries that we pick, will make one material to be able to store more material than the other one, and we make all sorts of tricks, like making one material bigger in volume to basically put it there. Just like when you are, I don't know, if you are having a party and you have to change from one house to another house, one house may be bigger than the other one, say, and if in one house you're having 15 people very happily partying and you move it to a big mansion, then you will be all spread out across the room or the rooms, and you will have much more space to put more people in it. Okay, so it's, in that sense, you want, well, not in case necessarily for a party, but for a battery, you want to be able to have those ions as they move from the anode to the cathode to be optimal, because if you have one material to store much more than the other one overall, you will have a waste of mass that will lead eventually to some economic losses, which if you are making a battery, you don't want to have. Okay? So how do we relate that solubility limit to the charge of the battery? Well, for each phase of the battery, okay, we have our solubility limit, okay, again, in moles per meter cube, okay, the volume of the electrode, okay, how much volume that mass is occupying space, okay, the electronic charge, are we using it, okay, times, in this case, the valence of the electron. Z times E is telling us how much of those ions are actually being converted into charge, because for Z of S species S, we have Z electrons, okay, and we have this little number over here called Avogadro's number that is allowing us to convert from moles to actually number of ions, okay? And well, typically people don't write E times Na, even though electronic charge, it's a fundamental constant, and Avogadro's number as well. Instead, what people do is they just use Faraday's constant, which is just a product of those two. Okay, and if you do that, you will get a measure of how much charge you can store there. You can think already, you can see already that if you want to improve your battery, you want to maximize that number, okay, as we were discussing in the previous slide. Or if you have some limitations, you want to make the volume of that material bigger in order to compensate, okay. Now, when you buy a battery or you're working with someone working on batteries, typically what happens is that that charge of your battery is not reported in coulombs, although naturally this will give you units of coulombs as it was written. Instead, they write it in terms of milliamps times hour. Why is that? Because as we have been developing technology to use it, we want to know how much current over a certain period of time in a human scale, in hours, we can use that battery for. And these are the natural units of as it's being used by the community. Now, this number is something you would get out of the chemistry, but that directly translates as to how that impacts in the response of the device by integrating how much current between the initial time to the final time, the current density across that time times the area. That will give you effectively the charge that we have moved from anode to cathode and back, okay? And in both cases, this one gives you material property of the system, and this one gives you what you actually effectively use. Okay, this one includes all the losses associated with the system. So now that we have defined a quantity that describes effectively how the material behaves, okay, we can actually start making lists of what we would like from that chemistry. Try to go through all the possible materials that exist or that can be designed to improve on that response. So basically what I'm saying here is that there is here a wish list that we would like to address, right? If I were to make a battery, what would I like from that material from the point of view of voltage, as we learned last class, and charge, as we're learning today? Effectively, we would like that both materials, okay, ideally, their charge should be balanced, assuming their volumes are the same, right? Basically, we want that the solubility limit times ZF of the cathode should be balanced by the solubility limit of the anode. Okay, this is important because if you have a cathode that is very energetic, the thickness of that cathode will be very small as compared to the thickness of the anode if the anode is very fluffy and cannot store a lot of mass per unit volume. So that has some implications as to how bulky your battery could be. Okay. And of course, independently for both cathode and anode, you want that solubility to be as large as possible. Okay, it's not the same to store 1 mole of charge in 1 cup than store 1 mole of charge in 1 micron by 1 micron by 1 micron. Okay, it's very different as to what you will store the same charge, but the space that it will occupy will have some impact in the application. As we were also discussing last time, there is a voltage difference. We want the voltage difference between the anode and the cathode to be as large as possible. Ideally, we will not only want this one to be small, we want this one to be as negative as possible with respect to the reference, and the voltage of the cathode to be as large as possible with respect to the reference, so that phi C minus phi A would effectively give us a large potential with a large charge. And we want both of them to be true, right? We want large voltage and large charge overall. So if that's the case, what you really want is to define a figure of merit that allows us to specify at the same time large potential and large amount of charge. And well, it's very easy to just think of, well, what I could do to a first approximation is if I want large voltage in the cathode and large amount of charge in the cathode, something that will give me large number of both of them is just a product of both of them. Okay, and that figure of merit happens to be actually the energy density, right? You can see the voltage of the cathode times the solubility limit times ZF effectively gives me the energy of the system, or, well, assuming that the voltage of the cathode is very large, okay, I can ignore phi A, and if both my cathode and my anode are balanced, then I only need to multiply by either of them. Okay, and effectively you can see this number will ideally give me that large value that I could use just by looking at, say, tables of cathodes and anodes as I pick voltages that they deliver and capacities that they can store. In practice, it's never like this, okay? What happens, however, is that, well, if we plot charge, capacity in this case, in a per unit, in a per kilogram basis, in the x-axis versus material potentials, in this case with respect to the lithium reference, okay, we find that all the cathodes actually have different numbers. You can see here for lithium-ion batteries, you can see here the manganese metal oxide systems will have very large voltage, above 4.4 volts. Okay, you have the manganese oxides, MnO2s, down here around 3 volts. And notice that if I have, at least the way this plot is sketched out, the material that has a large voltage will give me a lower amount of charge with respect to how much a lower potential could give me a higher capacity in comparison. The vanadium oxides, you can see, you won't gain much, right? You will get you will get a wider range of voltages, allowing me to jump a little bit, maybe for 500 millivolts, but not enough to actually give me some boost over there. And something that people have been doing recently is just start with ternary and higher order compounds. So you can see here a lithium, nickel, cobalt, metal oxide, where M, the metal, is magnesium, aluminum, and basically different dopants, just to try to go from this corner of 3 volts to try to push it up all the way here to 4 volts. Okay, and in this page you can see you have different selections that you can go from 100 amps hour per kilogram to roughly 300 amps hour per kilogram. Okay, that's the cathodes. Okay, the anodes are almost an order of magnitude above what an anode may have. In fact, the most widely used anode, graphite, you can see here, doesn't even fall on top of any of the cathodes. Okay, it's already far away. The capacity of the amount of mass or the amount of lithium you can store in an anode could be up to 4 times more of what you can store in the cathode. Making it, if you just have a chunk of cathode material, you have to basically shave by 1/3 the amount of anode that you will have in order to balance how much charge goes from one side to the other one. There are different materials that are being explored. You can see here, well, besides cathode, you can see different carbons that allows you to push the envelope even further. Some tin and tin oxide based systems, some 3D metals and nitrides, and the most energetic material of all would be the pure lithium, because see, you cannot really put more lithium than having a chunk of lithium itself. So really you can see here around 3,900 ampere hours per kilogram. If you compare it to the roughly 150, 200 ampere hours per kilogram, it really gives you a huge difference on how much you can store here and over there. Why is it that lithium metal is not being used these days as much as graphite? Again, the most widely used material. Why is it that graphite is the material that is used the most? There are a lot of safety issues that even after more than 20, 30 years of using rechargeable lithium-ion batteries have not been able to resolve with lithium metal. For reasons that will become clear in future lectures, lithium metal develops these growth called lithium dendrites that can make the battery unstable, forcing favoring the battery to become in an unstable state and therefore exploding, or developing, if you're lucky, an internal short circuit. So in order to avoid that, people have been using graphite as the reference, which gives you a lower capacity, but it allows you to avoid all the shortcomings that the lithium metal may have. And of course here the materials that have been used the most, lithium cobalt oxide, lithium nickel cobalt metal oxides. These are the sections where you would see the most being used these days. People these days are aiming for higher voltages, and always you can see where you would like to be in this map is up and to the right, basically above as you can as the highest potential and highest capacity systems, so that you can get the highest possible energy out of and charge out of your system. That's what ideally you would want on this map. Now, if you compare that to the figure of merit that we were describing on the previous slide, we were really referring to the area occupied by the system. Okay, and here you can see the voltage times the charge will give me how much of that material I can get. And if I really wanted to make it a good battery, I would try to compare against these reference where I would have to shave off, remove how much the voltage of the anode will deliver in order to effectively have an internal area in the space that gives me the energy that the battery is giving me. Okay, so I guess what you really want is a battery that occupies as much area in this map, okay, and where the anode doesn't take as much area as you would. Okay, now people don't necessarily use batteries in its pure single crystal or solid form. What they actually do instead is they make the battery in a powder form. They basically grind them into particles. There are lots of advantages for this, specifically because the lithium doesn't actually diffuse at a fast rate through the solid phase. And here you have an anode phase, a separator, which is the layer that divides the anode and the cathode. And the cathode phase in this case, I think, is lithium manganese oxide. In both cases, you can see they're made into powder form so that when you put the electrolyte in between, the electrolyte having high conductivity and diffusivity would allow for fast transport between the anode and the cathode. Okay? And another advantage of putting in this powder porous form is that the more area you put, you enhance the reaction. You will have more area for the reaction to take place per unit volume, and therefore it does give you some opportunity. So the relationship that we derived, this relationship will not be valid anymore. We have to do something about it in order to account for that porosity. In fact, that porosity, besides increasing the reactivity per unit area and adding additional transport parts to deliver charge faster into the system, it also gives us the opportunity, the disadvantage is that it gives us the negative aspect of that material is not being usable anymore. And as a result of that, we will lose some mass, some charge associated with that contribution. And usually that porosity is defined as a volume fraction left by the active material, okay, in a per unit volume basis, okay? And so a porosity of 0 means we have basically solid material without any pores. A porosity of 1 is all we have is electrolyte left there, okay? And we want to include this number epsilon as it's defined we want to tune it so that we can increase the reactivity, but at the same time we don't compromise too much on the charge density. Now, there are several porosity contributions. Okay, turns out that electrons, in order to reach a particle of active material, you have to mix the electrolyte with an electronic conductive phase. Okay, so here you have, in this sketch, this carbon phase that where the electrons are basically traveling, mix in the white region with an electrolyte. And in this case, the electrons travel very happily through the graphite phase, but do not travel through the electrolyte because the electrolyte is insulating. And so those electrons get to this point at a rate that is much faster than those by the lithium ions, and then they react at that interface with the reaction we just discussed. So this graphite phase adds an additional porosity contribution because we're not only not putting active material there, we had to put electrolyte there, and we have to remove part of that electrolyte so that those electrons can travel. If you think about it, the matrix between the particles of active material and its surrounding, it's bicontinuous because I want a path always to touch every single particle for both electrons and lithium ions. Okay? If I put too much of this graphite phase, what's going to happen is that my lithium ions will not reach the particles. If I put too little of this graphite phase, no electrons will reach this particle, and also my battery will not work properly. So you have to tune that very carefully, and as a result of that, I guess the bottom line is we need two routes for the ions and electrons to flow in the battery, so we need to add that conductive carbon, which adds an additional porosity contribution. And sometimes you add not only the electrolyte and the carbon, you also may add some other things, some fillers and binders to make the material, the battery composite now, to be not only suitable for exchanging electrons, but maybe you want to add something there to retard a fire to occur. Okay, and those will occupy additional space and will decrease and impact the energy density. So how is that accounted for? Well, it's, as it turns out, when you're making a battery, because you're making these really, really long rolls of material, you don't care much about the cross-sectional area, since this is you can think of it as a 2D cross-section of a 3D object. You care more about the thickness of the system, okay? And for that, you care enormously then about how thick the anode and how thick the cathode are, okay? So if I do this in a per unit area basis, okay, since they're all sharing the same area, I want to tune the thickness of the anode H sub A so that the charge in the anode balances the cross-sectional area, the amount of charge that the cathode may have, okay? So what we had before, now we have to subtract, instead of having a volume here, we're referring to the thickness, and instead of having just a number of 1, we have to subtract the porosity associated to the cathode material and the porosity associated to the fillers and any other conductivity that you may have in it, okay? And this number will decrease by that amount the charge of the system, okay? You can do the same thing for the cathode, or you can also do the same thing for the anode, okay? And if you think about it, this will compromise the charge in your system. Typically, these numbers lie between 30 and 50%, so that we can actually access the material. And so you can think of it as, just so that we can use the material, we compromise with nature by saying, here, take 30 to 50% of what you could do so that I can actually use you. Okay, so we lose 30 to 50% capacity of the system just from doing that. Okay, that said, you can still tune it. Right now you can see it depends on the thickness of each layer and on the material that we picked in order to specify how much charge we're getting out of this. Okay, now this is still specified. If before the charge was specified in milliamps hour, and now, because we're doing this in a per area basis, now this charge can be defined as a milliamps hour per meter square, okay, because we basically took out the area contribution to that. Okay, from the design point of view, now these two quantities have to be tuned, assuming that we don't have control over CTC and CTA, the solubility limits. We need to control by either controlling the porosity or controlling the thickness of each layer. And for that, we can define this quantity called the capacity ratio, which is effectively the ratio of both. As you can see, a well-balanced battery will have an R sub C equal to 1. Why? Because that means that the amount of charge that I'm taking from the anode is effectively being moved to the cathode and back. In practice, that doesn't necessarily happen because sometimes we want to leave some material behind in either of them to improve stability. However, you can think of a very neat figure of merit where if you cannot control, if you basically have already fixed what chemistry you're using for the cathode and the anode, by controlling the porosities or the thickness of each electrode, you will get the response that you want, okay? And this quantity, together with the measure of voltage and charge, gives us already a back-of-the-envelope way to select materials and how we can use them for future applications. Okay, and I will talk more about that on the next lecture. Thank you.